Okay, this is a recap video on beam bending moments for Principles of Mechanical Engineering. First thing you need to do is let's look at a beam that we're going to calculate for and then look at how we would do it. So we're going to look at first at a simply supported beam. So that is a beam that is supported by a pin joint or a roller joint at either end, and we're going to make our beam subject to some loads. So we'll have a downward load of 10 newtons, an upward load of 5 newtons, and a secondary downward load of 20 newtons. If it doesn't give you it already, you will need to find your reaction forces from the pivots. So check out the other recap video if you're uncertain of how we do this. So having calculated the reaction moments, it may be useful to redraw a diagram including all the forces and their distances. So it may be useful to redraw as a skeleton diagram where we've got our forces marked on, and the distances from the left hand side marked on underneath. Okay, then we need to consider what the bending moment would be in our beam. Now the bending moment is a reaction to, is an internal force within our beam. And we find this by taking cuts anywhere where the beam is under a critical load and considering the moments on one side or the other. We typically tend to consider the moments to the left of where we make our cut, and the convention is that a moment that was causing our beam to sag, ends go upwards, middle go down, is considered positive. A moment that causes our beam to hog, where ends go down, middle go upwards, is considered negative. So we look at the forces where they're applied, and we consider the moment they will do. First thing we're going to do is we are going to take a cut at 0 meters. Cutting our beam at 0 meters, there's one force applied, which is the reaction from A, but its distance is 0, so the moment is going to be 10.625 times the distance is from our cut, which is 0. And that is something that you will notice a lot. In fact, we can neglect taking cuts at the ends of our beams because it will always be 0. Then what we do is we then take cuts at all of our key points. So we're going to cut at 0, we're going to cut at 2, we're going to cut at 5 metres, going to cut at 6 metres. So cutting at 2 metres, we draw out our beam with our cut taken, and the cut is going to be, we include the forces that are acting to the left of our cut. So we can see there is a 10 Newton force, but it's acting on the cut directly, so its moment will be 0. There is this 10.625 newtons acting upwards at 2 metres away. So the bending moment at 2 is going to be positive 10.625 times 2. Take away. Now, here it will cause this end to bend upwards, so that's why we would have a positive sign here. Our 10 Newton force, that's going to cause our, that is a moment. The moment of that would be acting the other way, so it would be negative. We put in that times its distance from the cut, which is 0. So we get 10.625 times 2, which is 21.25 Newton meters as our bending moment at 2 meters. Then we finish off our other cuts. So we cut at 5 meters. Considering the forces and the moments they have. So our bending moment at 5 meters is going to be this 10.625 Newton force from A. That's acting over the whole length from our cut, so the moment it exerts at our cut is going to be 10.625 times 5, take away 10 into, now this force of 10 is acting 3 meters away from our cut. So the moment it contributes is minus 10 times 3. We find that our moment at 5, bending moment, is going to be 23.125 Newton meters. And our last cut is going to be taken at 6 meters. So cutting at 6 meters, we consider which forces are acting. And how far they are from our cut when we're considering the moments they are applying. Now at 6 meters we've got our moment at 20 Newton meter, 20 force of 20 applied. So what we do is we calculate our bending moment contributed by the forces to the left of our cut. We're going to omit the 20 because it's got a 0 lever arm, so we've got a positive moment contributed by our reaction force acting at a distance of 6 meters. Then we take away the 10 newtons acting at a distance of 4 meters from our cut, and we're going to add on the 5 times its distance of 1 meter. we find that our bending moment is going to be 28.75 Newton meters. So we've found all of our bending moments where our forces are applied. Then our next step is to plot those on a graph. So on our piece of paper we're going to plot our bending moment diagram. So to do that we need to set ourselves some axes. Now the largest bending moment we are going to experience is about 30. So we're going to, and we notice that all of these are positive, all our bending moments were positive. So we're going to draw ourselves a set of axes, then we're going to plot our points. So we're going to plot on our axes. This bottom axis is going to be the distance from the left hand side of our beam measured in meters. This axis is going to be our bending moment measured in Newton meters. A good diagram will always have these labelled. Then we take our bending moments that we calculated and we plot these on our beam. So the easy ones to do are the ends. The ends of a beam that is simply supported is always going to be 0 at 3 ends. Then we look, our first cut was at 2 meters, so move along to x equals 2, and it had a value of 21.25, so we are going to plot that on our graph. Then the next cut we made was at 5 meters and we found a bending moment of 23.125. Then our last cut we made at 6 meters and we found it had a bending moment of 28.75, so about there. Normally in an exam they would give you a piece of graph paper so you can plot these a little bit more accurately. And then we know at the end of our beam it's back down to 0. So then all we do is we join these with straight lines. For point loads you may expect straight lines between our bending moments. In the case here where we've not got exact markings, we are going to just mark on each point its bending moment. And we're done. What does this tell us? This tells us that our moments will increase and they're going to be highest at the point where 20 newtons is applied. So if our beam was going to bend, it would be bending there the most. If our beam is going to break, it's most likely to break there.